Okay, good evening. So we are going to have a revision on pure bending, and we are going to have also a revision on shear force and bending moment diagrams. Okay, so I understand that some of you are worried that you cannot remember what you learned for 2P. As I said before, don't worry. Then the next thing that we'll do is we're going to go for centric, symmetrical, and unsymmetrical bending. What does it mean to be symmetrical and unsymmetrical? Today, I understand that we have a tutorial from I think from 8 to 9, but no, I'm going to lecture all the way, and I'm going to do some examples, so it's going to be a hybrid lecture tutorial. Okay, so let's look at pure bending. Okay, as I said, this is a revision, so some of you might not remember. Okay, as some of you do, is good, so I'll have to revise with you. So let's look at pure bending. So when we have a structure that is simply supported, okay, so this is our beam. This is a pin, okay, and on a pin on the other side, you usually put a roller, right? And then we have a force applied on the center, which we call P, okay? And then we have our respective distance from one end to the force P is L/2, and from the other end is also L/2. Okay, so where the pin is, this is our point A, and this is what I like to call our point B. The force P is at point C. Okay, so when a structure is pinned, it means that if I were to sketch a transformation, this is X and Y, and we go about over here rotation about Z, Y anti-clockwise because we comply to the right hand rule. Okay, so at point is pinned. When we say it's pinned, means X motion is equal to 0. We don't allow movement in X direction. Likewise, we did not allow the movement in the Y direction. Okay. At point B is what we have called a roller. Okay, a roller restriction. So what it means over here is that X is not equal to 0. So i.e., we allow linear motion about the x-axis, but Y is equal to 0. Okay, so when we construct our free body diagram, okay, when we construct our free body diagram, okay, so we are aware that over here is where our P is. So for the fact that at point A, we don't allow motion in X or Y. So if you were to restrict motion, there is a reaction. Okay, then you can stop motion. So for this case, you will have a reaction, which is your AY. So the AY over here is to restrict at point A the structure from falling down, and over here we will have AX. Okay, so the structure will not move in both Y and X direction at point A. However, at point B, because Y is equal to 0, we only will have one reaction, and this is our BY. Okay. So if you have a structure that we have just sketched, this is what we call simply supported, right? So at point A, you have a support. At point B, you have support. So we usually classify this as simply supported structure. Okay. Where will failure occur? Anyone? Is failure going to occur at point A, or is failure going to occur at point B, or is failure going to occur at point C? Anyone, please. Where will failure occur? Or you can type on the chat. I can see likewise. Any idea?
Presumably
at
point C.
Yes, you got it right. So failure will occur at point C, right? And later on, we're going to show why, or I can tell you why, because maximum stress, normal stress will occur again at point C. Okay, so how do we calculate this maximum stress? Okay, maximum normal stress. So there's a formula that I'm going to write down for you, which you are all going to be familiar with or somehow seen it before in 2P. If not, not to worry. You have stress X is equal to minus mz over izz multiplied by y. Okay. So what we have over here, okay, I'm going to verify what they are. So this is the first formula that you have seen it before. Okay. So just to help you recap, okay, sigma x represents the normal stress in the x direction. So we can, our units, we can have it in Pascal or pounds per square inch, PSI. I want you all to get used to both SI and imperial units because it's Canada. Okay, we work with everyone and anyone. Then we have MZ. So MZ, it means applied moment in the Z direction, or in the, or along the, not in, is along the Z axis. So over here, our units is in Newton meter, or we have in pounds inch. Okay, and then we have IZZ, which represent the second moment of area about the Z axis. Again, units over here, it can be in meter to the power 4, or it can be inches to the power 4. And Y over here represents the Y distance from the centroid. Okay, so the units over here is in meter, or it can be inches. Okay, and then I'll write out the what does second moment of area means. Okay, so second moment of area in a layman's term, by looking at this equation where stress x is equal to mz over izz multiplied by y. Okay, another way of referring to second moment of area is the resistance to bending. Okay, so if someone asks you what do you mean by second moment in this formula over here, okay, is the resistance to bending. Okay, so I'll write up the mathematical representation over here. Okay, so the mathematical representation of IZZ is equal to width multiplied by depth to the power of 3 divided by 12 plus by area multiplied by capital Y bar minus small y bar squared. Okay, so this is the general formula that we see. Katie, is my answer okay for you? By what does that mean on second moment of area? Are you okay with that? Okay, thank you. Okay, so over here, the capital Y bar is the centroid of the global structure. Okay. Later on, when we do an example, you'll see this clearly. Okay, and it's in meters. And small y bar is the centroid of the individual section. Okay. So again, this formula over here is important. Okay. These formulas are important. Right. So I've shown you a relationship that the normal stress X is equal to minus mz over izz multiplied by y. Okay. Now the next thing comes to your mind. Okay. Comes to our mind is why do we have a minus sign over here? Okay. Why must it be minus? Okay. And there are a few explanation that I can give, but I'm going to show you how this minus play into determining whether the structure is under tensile or compression. Okay. So what I like to highlight is over here is when stress X is negative, it means it's under compression. And then when stress X is positive, it's in tensile. Okay, let's get this out of the way first. Okay, right. So when we look at our structure, okay, now we go back over here. We look at our simply supported structure. I'm going to sketch for you the deformation pattern. Okay, we're going to look at the deformation pattern. So you have a load applied at the center at point A and point B is a support. So now next, I'm going to sketch the deformation pattern. And I want you, I need all of you to be able to sketch the deformation pattern is because we are not going to rely on the positive or the negative of the formula. Okay. In this course, a key feature that I want you to see, or I want you to learn from me to embrace this knowledge, is to physically physically guess. Okay, what do we mean? Where the tensile and compression will occur? To me, I think like that is really important. Okay, so what do I mean by that? So we know that we have a load applied at the center. So if we were to sketch the deformation pattern will look like this. Okay, so this is how the structure will deform, right? So the structure will deform in that way. So we know, right, down here, I'm going to pick a point over here. And this point represents the center of curvature. Okay, the point that I pick is known as the center